Okay, happy day and welcome. So what we're going to be doing today is we're going to be talking about buffers again, but this is part 2 because now we're talking about how do you calculate the pH of a buffer, okay? And so there's this amazing equation. It is called the Henderson-Hasselbach Equation. There's a long way of working out the problems. You're going to be given a Ka value, so they're going to be weak acids and a salt, okay? And so what you're going to need to do is basically, the idea is similar to what we are doing weak acids or weak bases, and you're given a Ka. Anytime you're given a Ka, you probably want to write a what? And what? Equilibrium expression. Very good. So what you would do is you would write your expression, you have your equation in order to write the expression, and then you basically figure out the concentration of your H plus ion or your OH minus, if it's a basic buffer, so it can be an acidic buffer or a basic buffer. And then once you have that, you'll simply negative log it. So once you get your H plus, your OH minus, which is probably going to be X, it might be one of like the X values in your expression. So what Henderson-Hasselbach does is it gets rid of all of that. So I'm going to show you how you can work it out both ways, but it makes it a lot faster. It's a super shortcut if you know it. They give it to you on the equation sheet, which is also really nice. They don't give you the basic one, they give you the acidic one, okay? And so if you're calculating pH, we're going to say this together. We did this before, so it's going to be pH equals pKa plus log of Cb over A. I like this version. They give you this on the equation sheet. The reason why I like this is because the conjugate base is your A minus. And a lot of times people will look and go, what is A minus? Well, HA is your acid. So if you have your acid, remember acids always start with a hydrogen ion, right? So this is the acid with your hydrogen, and this is when the hydrogen has come off and it just becomes your A minus, which for example, let's say it was acetic acid, then it would be HC2H3O2. So what would your A minus be? C2H3O2 minus, okay? And so that's how that works. Or I like saying conjugate base and the acid because I feel like people can recognize that pretty easily too, okay? So here we go. Everybody's going to say it with me. Try not to look. If you've done it a few times, try not to look. Here we go. pH equals pKa plus log of Cb over A. Now we're going to try to do what would it be if it was POH, okay? So if it was POH instead, how would this be different? Ready? POH equals pKb plus log of Ca over B. Perfect. So then it would be Ca over B instead. You can see that it still pretty much rhymes as well. And then we also want to make sure that we remember, how do you make a buffer? This is going to be really important. How do you make a buffer? It's super easy. You either have a weak acid and its salt or a weak base and its salt. So I want to make sure that you understand, what does its salt mean, okay? And all the salt is, for example, if you have something like HF, it's a weak acid, right? Hydrofluoric acid is a weak acid. Give me any salts. What do you think the salt would be for HF? NaF, I like it, okay? Or LiF or KF, okay? So anytime that you're going to have one of the, usually an alkaline metal is what it's going to be with, and then with the ending, okay? Or you can have a weak base with its conjugate acid, which means it's salt, okay? So right under here, I just want you to write with its salt. And then same thing here with its salt. Okay, so that's what they're going to call the salt. Okay, so these are a couple of review problems. I want to make sure that you remember how to do these. So letter A says, we have a liter of pure water and it's at a pH of 7. If you add 0.1 moles of NaOH to it, what is the pH? Okay, so we know that in order to figure out the pH or the POH, then what we need to do is, what's the equation for POH? POH is equal to negative log of OH minus. So if I know my hydroxide concentration, then I can figure this out. Well, it's 0.1 moles, but that's not the molarity. What's the molarity? Moles over liter, but it's still the same, right? It's 0.1 over 1. So it's still 0.100 molar, okay? Because we're going to divide it by the 1 liter, and we get 0.100 molar. NaOH is going to break up into what? Na plus and OH minus. So if I know that my NaOH is 0.1 molar, what's my OH minus concentration? It's the same. It's a 1-to-1 ratio. Okay, so we know it's going to be 0.1 molar. Completely dissociate, so it's going to be 0.1 molar. Okay, So then all I'm going to do is I'm going to say it's equal to negative log of 0.10, and that, which is 1 times 10 to the negative 1. So my POH would be equal to what? What's the negative log of 0.1? 1. Perfect. So it's 1 times 10 to the negative 1. So remember, it's whatever your exponent is. So if it was 1 times 10 to the negative 5, your POH would be 5. If it's negative 9, it would be 9. Okay, so it's whatever your exponent is. So that's 1. I want 2 sig figs, though, so I'm going to do 2 zeros after the end. That's my POH, though. They asked me what the pH is. So what do? Subtract from 14, and I get 13.00. Does it make sense? Can sodium hydroxide be a pH of 13? Yes, it can. If it doesn't make sense, what would you say your pH is? 7. Perfect. If it doesn't make sense and you're like, wait a minute, it's a base, it should be higher than 7, and you get 2, you know that it's wrong. It should just be 7. But double check, because some people will forget to subtract from 14 in that case. Okay. So for B, a little bit different. Now we've got, instead of NaOH, we have CaOH2. Okay, so I'm going to do the same thing. My POH is equal to my negative log of OH minus, but now what is my OH minus concentration? Very good. It's 0.1 times 2, which is 0.2. So this is actually 0.2 molar. So now I'm going to do negative log of OH minus, which is 0.20. Please plug it into your calculator and tell me what you get. Oh, I have my calculator too. So negative log of 0.2. And we should get are you getting 0.699? Yeah. Okay, so I'm going to say, because I want 2 sig figs, I'm going to say 0.70. Okay, so I'm going to get 0.70. Again, that is not my pH. My pH is, sorry, that was my POH. My pH is, what? 13.30 is going to be my pH. Perfect, okay? And remember, only when you're doing pH and POH, only the numbers after the decimal count. So people will say, wait a second, Mrs. Ismail, you just went to 4 sig figs. No, I did not. That is still 2 sig figs. That's 2 sig figs, and that's 2 sig figs because it's only the numbers after the decimal that count. Good? Okay, only for pH and POH. For concentrations, it's normal. Okay. All right, then it says part C, what is the pH of a 4 times 10 to the negative 12 molar CaOH2? Okay, so we're going to do the same thing. We don't have to really write this, so this was part B. So for C, we don't really have to write this all down. We're going to negative log that. So let's negative log 4 times, not 4 times 10 to the negative 12, but what? 8 times 10 to the negative 12. 8 times 10 to the negative 12. And I'm getting for this one that my POH is equal to 11.10. So that's my POH. So what do I do to get my pH? 14 minus answer. And I'm getting that the pH is equal to 2.90. What? I'm seeing no's. What do you mean no? Why not? It doesn't make sense. It's a base, so the pH should actually be what? 7. So if you see, it's pretty easy to see. If you see that this is bigger than 10 to the negative 7 for a hydroxide, that's not going to make sense because that's such a small number. That means that your solution is basically just what? It's basically just water. Okay? So if you add that much of a calcium hydroxide into water, it's really not enough to call it a base. It's pretty much just water. And that's what the idea is if that number's either too low or too high, depending on if it's an acid or a base, then just make sure it makes sense. Okay. So now we've got a different question. It says, a buffer is prepared from 1 liter of 0.5 molar, I always like to underline things, of an acetic acid solution. So I know I'm seeing a weak acid. And by the way, sometimes they may not even tell you it's a buffer. It may not say it's a buffer, but if you see that it's a weak acid in itself, watch how you're going to see this, okay? And then it says I add 0.2 moles of NaC2H3O2. Look at this compared to this. People will want to react it. And if you go to react it, what are you going to say? What's the problem? There's no reaction because your anion is exactly the same. You have acetate and you have acetate. It's no reaction. So then people get confused and they're like, I'm so confused. What am I supposed to do? Okay. So we're going to do this 2 ways. We're going to do it using the Henderson-Hasselbach so I can show you how easy it is to use the Henderson-Hasselbach. And then I'm going to show you how to do it the old style if we were using the Ka equation. Okay. So Henderson-Hasselbach, everybody's going to say it with me. I'm going to write it small up here, and then we'll fill in everything. pH equals pKa plus log of CB over A. Very good. Okay, so let's fill it in. So my pH is equal to, the P stands for what? Negative log. Very good. So I'm going to say negative log, and now I need my Ka value. And so it tells me the Ka of this is this number. Sorry, we forgot to underline that. So my Ka is 1.80 times 10 to the negative 5. I'm just going to minimize it so that I have enough room here. 1.80 e negative 5. Plus the log of, okay, which one's the conjugate base and which one's the acid? It's pretty obvious, right? Which one's the acid? The HC2H3O2, which means obviously this is going to be my conjugate base, okay? So I have 0.2 moles, but I don't want moles. What do I want? Molarity. We need molarity. This should be in brackets, and brackets mean molarity, okay? And it is the log of both of the numbers divided. So what do I do to get the molarity? Divide by 1. So it's just 1 liter anyway. People will say, yeah, but you just added those moles to it, so doesn't it change the volume? Remember when I did the paper clips in water, and you could add a whole bunch of paper clips and it doesn't really change the volume? So our volume's pretty much going to stay at 1. And a lot of times they'll say, it says it, assume there's no volume change, okay? So then it's just 0.2 molar. 0.200 molar is going to be my conjugate base. What about my acid? It's just 0.5 molar. Okay, go ahead, plug this into your calculator. I want to make sure we all get the same answer. It doesn't really matter which side you start on, but you do need parentheses around the 0.2 divided by 0.5, okay? All right, let's see what you get. Hey, and did you get 4.347? We want 3 sig figs because that's 3, that's 3, that's 3, so we're going to have 3 after our decimal point. And this is pH already. If this was a base, I would be calculating POH, so then we would just have to make sure that we subtract from 14. But this is it. Pretty easy, right? Okay, so now let me show you what if you didn't have the Henderson-Hasselbach and you wanted to do the calculation without using the equation. Again, the equation is brilliant, okay? So the first thing that I would need to do is I would need to write my dissociation equation, okay? How do you know which one you're writing it for? It's the one that you have the Ka for, okay? So the Ka I have for the HC2H3O2. So I'm going to write HC2H3O2 arrow H plus C2H3O2 minus. And now I'm going to write my expression. I'll leave a little bit of space underneath here just so we can do our X's and figure out our concentrations. Okay. So Ka, remember, is products of a reactants. If it's an acid or, well, specifically acids, they're aqueous. Okay. So you do have to actually include the denominator. So this is H plus times C2H3. Oops, let's redo this here. Got my bracket. C2H3O2 minus divided by HC2H3O2. Okay, so again, because it's aqueous, I do have to include that, where when we were doing dissociations for KSP, those were solids, when we were trying to figure out if it precipitates, for example. Okay, what do I know? So I know, pretend we didn't do any of this, right? I know that my concentration of my HC2H3O2 is 0.5, but it's not actually going to be 0.500 because what's going to happen to it? It's going to dissociate. By how much? I don't know, X. So if I call this X, then what should I call this one? X, okay? But this is actually 0.500 minus X, okay? We're going to assume that X is small, though. And if we assume that X is small, we can just call that 0.5, okay? So you're going to see how close we're going to get to this answer when we do this. All right, so then they say we add 0.2 moles, or 0.2 molar, right? Because if we divide by the liters, of the NaC2H3O2. NaC2H3O2 is going to do what? Completely dissociate. It's a 1A. Anything that starts with Na or Li or K, any of the alkali metals, you know it's going to completely dissociate. So this is not just X. This is going to be X plus what? Plus 0.2 molar. Plus 0.200 moles, but per liter is 0.2 molar. Guess what we can assume about that? X is really small. So I'm going to say that this is approximately equal to 0.200 molar, and I'm going to say that this is approximately 0.500. Okay, so now let's fill in what we have. I already know my Ka. It's 1.80 times 10 to the negative 5 is equal to, I don't know my H plus, that's X. That's what I'm looking for, right? Because once I know my H plus, I can negative log it to find my pH. So that's X. I'm going to multiply that by my acetate, which is 0.200 molar, divide it by my acetic acid, which is 0.500. Again, minus X, but we're going to assume it's small enough. Go ahead and do the math. I want you to see if you can figure out what X is, which is essentially H plus, so then we can calculate the pH, okay? So go right ahead and let's do our algebra and cross multiply and divide. Okay, it looks like we're getting 4.5 times 10 to the negative 5, but I still want 3 sig figs. So I'm going to say 4.50 times 10 to the negative 5. Now, to find the pH, what do we do, everybody? Negative log it. And so let's negative log this number. And if I negative log the number, oh, what? Surprise. What do you get? The same exact answer, 4.347. 4.347. Okay. I will say that most teachers don't even teach this. They just say the Henderson-Hasselbach is what works. Memorize it. If you have a weak acid in its salt or weak base in its salt, just use it. But I think it's nice to see that you could do it the long way. Obviously, it takes way longer, right? And you're more likely to make some mistakes doing it this way, but it does work. Okay. All right. So remember, the purpose of a buffer is to maintain a nearly constant pH. So it says, when you add acid to a buffer, what do you think? I want you to just think about it because there's going to be a problem, okay? We know that buffers are going to try to maintain a constant pH, but if you're going to add an acid, what do you think is going to happen to the pH when you add an acid? It's going to go lower. And obviously, when you add a base, what's going to happen to your pH? It's going to go higher. But since it's a buffer, it's not going to change by much. And so that's going to be kind of the big problem is where they're going to say, and sometimes they don't even have you calculate the original pH. They're just going to have you go straight into like, what is the pH after you've added the acid or after you've added the base, okay? And you can add acid to a basic buffer. You can add acid to an acidic buffer. There's no rule on that. You can do whatever you want, okay? So when you add acid to a buffer, we know the hydrogen ion increases, which means our pH should decrease. And then when you add base to a buffer, it's going to react with your hydrogen ion, which means your pH should actually increase, okay? So keep in mind that when you add an acid, it's not just going to sit there. It's going to react with the stuff inside of there, okay? And so it's going to essentially pull some of your base is what it's going to do, okay, when you add the acid. Okay. So we've got a 1 liter buffer containing 0.7 molar. So we've got 1 liter, fine, contains 0.7 molar, 0.8 molar. We don't really care about the liter now because they're not even giving us moles anyway. And then they're giving us the Ka value, and it says, what is the pH of the solution? Okay, everybody ready? Here we go, Henderson-Hasselbach, because I'm seeing an acid and it's salt. pH equals pKa plus log of Cb over A. Very good, and obviously in brackets, okay? So let's go ahead, let's fill this in, and let's see how we do. So go ahead and fill in your numbers, and then we'll see how we did with calculating the pH. Are you getting 4.803, something like that? We want 3 sig figs, 333. So remember what I want is I want 3 numbers after my decimal. So 4.8027 is going to become 4.803, and that is my final answer. Good? Okay. So now watch what's going to happen. It says you're going to add 0.1 moles of NaOH. And then the question is, how does the pH change? First, I want you to just think about it, because if this is a multiple choice question, what they're going to want you to do is to basically just give an estimated value, and they probably are going to throw their numbers. They're going to give you one pH that's higher than what you started with. So they're going to give you maybe one that's equal. They only give you 4 answers in the multiple choice. So they may give you this exact answer. They'll give you one that's a little bit higher, one that's a lot higher, one that's lower. Okay? So if you're going to add base to it, what do we expect to happen to the pH? It should go up. Okay? So we know that our pH is going to change and it's going to increase. By a lot or by a little bit? A little bit. Why? Because we have a buffer. We have a buffer, and that's the idea of a buffer, is it's going to try to maintain a constant pH. Okay. So the way that you're going to do this is I want you to think about, and I usually like to write out what my acid is and what's happening like with my acid and my base to kind of get an idea of what's going to be taking place here, okay? So I have my HC2H3O2, and it's going to react with the NaOH, okay? So if you do it the wrong way, you're going to know right away that you did it incorrectly, okay? But one side you're going to add to, and one side you're going to subtract from, okay? Because it's a reaction that's happening. So it's not just like, well, I'm just going to add to my base side and then call it a day, because one side has to add and one side has to subtract. Okay. Okay, so let's write this down. I know I have HC2H3O2 breaking up into H plus and C2H3O2 minus. Okay, and it's 0.1 moles, but it's only 1 liter anyway, so it's actually 0.100 moles divided by my 1 liter, which I know again is going to be 0.100 molar of my NaOH. Okay. So what is my base going to react with? It's going to react with which one? With the acid, right? Here's my acid right here. So I know that what's going to happen is this, I'm going to subtract my 0.100 from. And if I'm subtracting on this side, guess what's going to happen to my acetate? I'm going to need to add on my acetate side. Okay. So on this side, I'm going to say it's going to be, it was originally, let's put this in. So originally it was a 0.700. It's kind of like an icebox, basically. Okay. But we're going to skip the change. Well yeah, we're doing a change step. So it's exactly an icebox. So now I have my C2H3O2 was a 0.800 molar. And so now I'm going to say this side must be minus the 0.100, which means my conjugate base should be plus 0.100. And when I do that, I get 0.600 on this side, and then I get 0.900. So it's essentially an ICE, kind of, right? It's basically like doing an icebox. But we don't know what our H plus is. That's going to be our X. That's what we're looking for. Okay. Now that we have this, we can use the Henderson-Hasselbach again. Okay. We already wrote it down, so let's just go ahead and fill it right in. So my pH is equal to negative log of my 1.8, my Ka, 1.80 times 10 to the negative 5, plus the log. Now what's my conjugate base concentration? 0.9. Now my base is 0.900. And my acid is 0.600. Go ahead and plug this in, and let's see what we get. Okay, and did you get that your pH is 4.921 with 3 sig figs? So I want you to take a look at how it changed. We went from a 4.8 to a 4.9. I mean, really? Like, if you're testing this, if you're in lab, the difference between a 4.8 and a 4.9 is barely anything. Okay, so that's really not a huge change at all. Okay, all right. So let's take a look at this next problem. Let's see if you can do this on your own. So now we have a 1.5 liter of a buffer, contains 0.750 molar and 0.850 molar. Do we really care about the volume right now? No, but anybody see where it is going to matter? Where? Yes. When we go to do this right here, we may as well just do it now so we don't forget. Okay. So I'm going to take this and I'm going to divide it by my 1.50 liters. So we've got 0.25 divided by our 1.5, and we get 0.167 molar is going to be our HCl that we're going to add to it. Okay. They're skipping the first Henderson-Hasselbach. They're going right into, we've added this stuff to it. What's the pH? Okay. If you want to do the first part, you can, because the only reason why I would say to do that is so that you can check to make sure that you did it correctly. Because what do you expect to happen to your pH if you add acid? Your pH is going to need to go down, but I don't know what my original is. Again, you can check it real quick once you write your equation. Okay, so what I'm going to do is, which one is dissociating? What's my acid here? I need to know my acid and my conjugate base. So which one's my acid? The HBRO. And that's going to break up into what? H plus and BRO minus. Very good. And so my HBRO concentration we know is 0.750. And then what else do we know? BRO minus is what? 0.85. Perfect, because remember, this is a salt. And usually they'll start them with Na, which is really nice. You know it's going to completely break up, so this is going to be 0.850. Okay. But we're going to add acid. So what is the acid going to react with? Is an acid going to react with another acid, or is an acid going to react with a conjugate base? With the base. Okay. So the acid and the base are always going to react with each other, which means this is going to decrease by how much? 0.167. Perfect. So this is going to be minus 0.167, which means on my acid side it is plus 0.167. So now let's do our kind of like equilibrium step. Okay, so I've got 0.75 plus the 0.167. Oops. And that's giving me 0.917 on this side. And then the 0.85 minus the 0.167 is giving me 0.683. Guess what you're going to do with these numbers? Plug them into the Henderson-Hasselbach, okay? So let's go for it. pH equals the negative log of the Ka, which is 2 times 10 to the negative 9, plus the log of my conjugate base. Which one's the conjugate base? The 0.683 or the 0.917? 0.683. Divide that by the 0.917, and then let's see what we get for our pH. Okay, and it looks like 3 sig figs? 2 sig figs because of the Ka. Perfect. So it looks like it's going to be 8.57 as our final answer. Okay, awesome. Very good. And that is it for Henderson-Hasselbach and dealing with buffers. Happy day, everybody.